So let's talk about acid-base titrations. So a titration is a procedure that allows chemists to determine the concentration of an acid or base. And they do that by performing a neutralization reaction where the volume of the acid and the base are accurately measured. And then the concentration of one of the reactants, either the acid or base, is a known concentration. And so, with all that information, it allows the concentration of the other reactant to be determined using stoichiometry. So, this is the neutralization reaction. So, in a titration, the volume of both of the reactants is known, but the concentration of only one is known. And through stoichiometry, you can calculate the other one. So, this is how it's performed. The solution of known concentration, which is called the titrant, is placed in a burette, and then a sample of the unknown concentration is placed in a flask underneath the burette, and that's shown in that diagram. So the sample in the flask has a volume that was accurately measured using a pipette. So it might be 10 milliliters, it might be 25 milliliters, but it was accurately measured. So we know that volume. And then the burette allows for the titrant to be added slowly and precisely. So there's a little valve at the bottom that allows the chemist to control how much titrant is going in and how quickly it's going in. So the titrant is added from the burette into the flask, and the neutralization reaction is happening in the flask. And so it's added until the reactant in the flask has been fully consumed by the reactant in the titrant. So this is our reaction. So if we are adding acid to the base in the flask, we would add the acid until we have completely reacted all of the base. So all of the unknown has been reacted, and only the salt and water remain. So if we know how much we had to add to completely react, we can figure out the unknown concentration. So the point when all of the acid and base have reacted and there's only the salt and water in the flask, this is called the equivalence point, which for a strong acid and strong base is going to occur at pH of 7. The trouble is that the solutions of acids and bases are colorless, and the solutions of salt and water are colorless. So when you're adding titrant to the flask, it's just colorless, and you can't see what's going on. So how do you know that the equivalence point has been reached? So for that, indicators are used. So before you start doing the titration, you add a few drops of indicator into the flask. And an indicator is a substance that changes color beyond a certain threshold pH level. So this diagram shows a few of the common indicators, and it shows where they change pH. So something like bromothymol blue changes color at a neutral pH, whereas something like indigo carmine at the bottom doesn't change color until you've got a very basic solution. So when you're carrying out the titration, you add the titrant until the indicator changes its color. And when the color changes, that's called the endpoint of the titration. So it's important that you choose an indicator that's going to change color at as close as possible to the equivalence point. So you want the endpoint, the color change, to be close to the equivalence point. So it's a visual indication that the reaction is complete. So as I mentioned, during a reaction of a strong acid with a strong base, the equivalence point will be at a pH of 7. So we would want to use an indicator that changes color around a pH of 7. And so common ones that are used for this are bromothymol blue and phenolphthalein. So it looks like phenolphthalein changes a bit on the basic side, but it does work very well for this type of titration because you're trying to catch it just as the color changes. So you carry out the titration, you've got the measured volumes and the known concentration. So, how do you figure out the unknown? So, here's a sample problem. You're trying to determine the concentration of a solution of hydrochloric acid. You have a standard solution of 0.10 mole per liter sodium hydroxide available. So you perform a titration with 25 milliliters of the hydrochloric acid, that's in the flask, and you discover that it takes an average of 22.36 milliliters of sodium hydroxide to reach the equivalence point. So, what was the concentration of hydrochloric acid? So, there's our balanced chemical reaction, which you need before you can do any type of stoichiometry problem. And this is just like any other stoichiometry problem. This isn't actually anything new. It's just looking at it from the point of view of how the data is obtained using a titration. So you're first going to find the moles of the hydrochloric acid, and because you have the volume, you can then calculate the concentration. So start with the volume of the standard solution that was used, which was 22.36 milliliters, and we convert that to liters. Then you're going to find the number of moles using the molar concentration. You can also use the concentration formula here if you prefer. So that gets us to moles of sodium hydroxide. We need the moles of HCl, so we're going to use the mole ratio, which in this case is just 1 to 1. So that tells us that we had 0.002236 moles of hydrochloric acid in the flask. Now we can calculate the concentration with our formula. Concentration equals moles over volume. So we take the moles that we just calculated, we divide by the volume of the HCl that was used in the flask, 25 milliliters, which we convert to liters. When you do that division, you get an answer of 0.089 moles per liter. So that is the concentration of that solution of hydrochloric acid.